gonna work through the practice test, and then as long as we make it through all this today, then Wednesday will just be a day to come and ask questions. Maybe if you have Hawks questions you need help with, we can do that Wednesday. But other than that, we don't have a whole lot to do on Wednesday. Okay. All right, so going back to the beginning here. Number one says identify the population being studied. We're given the overall exam scores of 14 out of the 37 students in your biology class. So the population is the whole group that we're trying to learn about. So if we're given the exam scores of 14 out of the 37 students in our biology class, then our population will be all the students in the biology class. It's not all students everywhere taking the biology class because that's just too big. Okay, our data is only coming from our biology class, and then it's not the 14 students because that would be a sample. Now that would be a sample. Part C there. Okay. If you have questions, just let me know. I'll be glad to stop. Okay. Number two, we want to decide if we're looking at a population parameter or a sample statistic. So we just have to look at what the number is describing. Is it describing a sample or a population? So this one says 66% of all students at the local university voted in the last election. We don't have anything in here telling us about a sample being taken or anything like that. So our population here would be all the students at the local university. That 66% is describing the population. So this is a population parameter. In order to be a sample statistic, we would have to have something like, we'd have to have something about a sample in there, like 40 students were surveyed, something like that. And then 66% of those in the survey voted in the last election. The population parameter, though. Number three, we want to decide if we've got a descriptive or an inferential statistic. Now remember the difference. A descriptive statistic just describes the data. An inferential statistic takes the sample data and makes some kind of conclusion or some kind of inference about the whole population. So this one, we're given a survey of 1,374 people, revealed that 55% have a college degree. Therefore, it can be assumed that 55% of the U.S. population has a college degree. So since we got this part and we're making a claim about the whole population based on that, this one is an inferential statistic. That's like what we've been doing with the hypothesis testing. We've been doing inferential statistics. If it just said the first part, up till you get to the semicolon there, it would just be descriptive. Number four, and sorry, this one's kind of split between two pages here. We're wanting to classify this data. We're told that a business must keep a record of each employee's social security number. So the data is a social security number, and I'll rewrite that here, social security number. Well, that's really sloppy. Okay, we're looking for social security number. We want to know, would that be qualitative or quantitative? That one's a little bit tricky because it is a number. I know you know what social security numbers look like, but it is a number, but there's nothing really numerical about it, right? Like we wouldn't add and subtract social security numbers. That wouldn't make sense. They're really just a label. So that's a situation where we're using a number as a label. That one's a little tricky. That one would just be qualitative. And then for discrete or continuous, since it's qualitative, remember qualitative can't be either one. And then the highest level of measure, since it's qualitative, it's got to be either nominal or ordinal. So we think about, could we put social security numbers in order? And we could put them in numerical order. So this one would be ordinal. Okay. Number 5, same type of problem. This time we've got temperature in Celsius. So this time temperature would be quantitative. And then if it's quantitative, we have to decide would it be discrete or continuous, since temperature is a measurement. Usually measurements are continuous, because we can be as precise as we want to be, and we can go down to as many decimal places as we need. And then for the highest level of measurement, since it's quantitative, it's either going to be interval or ratio. So the important part here is that it tells us we're in degrees Celsius. Remember the difference here for ratio data. 0 actually has to mean the absence of something or the beginning of something. And on the Celsius temperature scale, 0 is not the beginning of the scale, and it's not the absence of heat or absence of temperature. So this one is not ratio, it would just be interval. Questions on that? Okay. Don't be shy. If you do have a question, just jump in. I know several of you are just here just in case. So anyway, but still. Okay. Alright, so we got a Pareto chart showing us the number of student blood donors by their blood type for one day. We want to know how many students donated blood on that day. This one is just as simple as we just add them all up. So we had 50, 35, 30, and 15. So let's see, what is that? 85 plus 45. Just totaling all these up. So 130. Nothing real special there, just reading the table, reading the Pareto chart. And number 7, we want mean, median, and mode. So for the mean, it's been a while since we've done one. We add up all the data, and divide by how many data values we had. If we add up all those, get 30. And let's see, we had 6 of them, so we get 5. If we're using our rounding rule, we would call it 5.0. For the median, we want the middle number. The big thing to remember is we want to put our data in order. So I'm going to do least to greatest. So let's see, -10, and then 4, and then 8, and then 9, 9, 10. And in this case, we've got 2 numbers in the middle, 8 and 9. So if we had that situation, we add the 2 middle numbers together and divide by 2. So then we'll get 8.5. If you just have one number in the middle, that's the median. Okay, and then for the mode, that's just the one that's on there the most. 9 is on there twice, so our mode is 9. And then we only have one mode, so that would be called unimodal, though I'm not really interested in asking that part, but our mode is 9. Okay. Mean, median, and mode. Let's see. Number 8. Got a empirical rule problem. I won't give you one of the hard ones. And this is just the one remembering the empirical rule. So Empirical rule says within 1 standard deviation of the mean, we got 68% of the data. Within 2 standard deviations, we've got 95%. And within 3 standard deviations, we've got 99.7% of our data. Put the 7 there. So this one says if we've got a mean of 104 and a standard deviation of 17, using the empirical rule, what percentage of IQ scores are between 70 and 138? When we did these, we drew it out. We can also use the Z formula now that we know what that is. We wanted to do 70 minus the mean. We could figure out how far away this one is. You can do it either way. You can sketch it or use the Z formula. Oh, what did I do? I'll see if I can do that. This one's coming out a little. Oh, because I wrote down 107 and it's 104, sorry. Yeah, so that's 2 standard deviations below. If you do the same thing on the other one, it should be 2 standard deviations above. And so, since we were dealing with 2 standard deviations away from the mean, that one will be 95%. Again, I won't give you one of the harder ones where you have to use the symmetry and all that. So. Number 9 is calculate the interquartile range. So to do that, we've got to get the quartiles, and I wish I would have remembered to put this data in order first because we need to do that. But let's see, so 4, 6, I believe, is next. And we got another 6, and then a 7, and then 9, 13, and then 23 and 24. And then 30, 37, 39, 44, 45, 55. Looks like we got everything there. So first thing we want to do is find the median, get Q2. So let's see. On this one we've got 2 data values in the middle. If we wanted to find Q2 exactly, we would add 23 and 24 together, get the median. This one, since we're not actually having to find all of not all the 5-number summary, we just want the interquartile range. What we really want is Q1 and Q3. So as long as we know where to split the data, we're in good shape there. So then Q1 will be the median of the lower half of the data, 7. Q3 will be the median of the upper half of the data, 39. And then to get the interquartile range, we just subtract. So 39 minus 7. Interquartile range is 32. Takes more work to put them in order than it does to find the interquartile range. What number? Number 10. 10 says find the expected value. So that's a formula that will be on the formula sheet, but also you can just remember how to do it. We just take each outcome, multiply it by its probability, add all those together. So This one, then it'd be 6 times 0.3 plus 7 times 0.2 plus 8 times 0.1 plus 9 times 0.2 plus 10 times 0.2. And let's see what we get there. I'm getting 7.8. That's all the stuff from test 1. We're slowly getting more recent as we work on these, so probably the rest of this will be more familiar. Maybe confidence intervals are a little rusty on those. 11 says calculate the standard score, so that's x 42.4 minus mu 48.2 divided by sigma, which is 50.6. This is around to 2 places. This one I'm getting negative 0.11. Alright, then we got table drill. We got all these chapter 6 area under the curve problems. So let's see. First one says find the area under the normal curve to the left of 1.72. So since it's to the left, we just look it up. Go to the z tables, look up 1.72. Now when I get 0.9573. Mm. 13 says find the area between these two z's. So to find the area between, we just look both of them up, and then we subtract the areas. So first one we got negative 0.57. Let's see, negative 0.57. Get 0.2843. And the other one is 2.3, so that would be 2.30. 2.30. We get 0.9893. And our answer can't come out negative, so we want to put the bigger one first. And subtract. So 0.9893 minus 0.2843, 0.705, or if you wanted to, you could add a 0. Since we normally use 4 places. Mm-hmm. 14, these are the inside-out problems. And I know that because it says find the value of z, so my answer's got to be a z. So these are the ones where we look for the area inside the table and then read it inside out to find the z. So this one we want the value of z so that we've got 0.01 of the area to the left of z. So we got some z value. And the area to the left of that is going to be 0.01. So I can look inside the table at the areas. Look for 0.01, or if we want to, we can add 2 zeros to that. And this one's not in there exactly, so we just get as close as we can get. The area I'm finding is 0.0099. That's the closest one. And that gives me a z-value of negative 2.33. Find out one's there. Number 15 is almost, or it is the same type of problem. It's just we're just dealing with our area. We want our area to be to the right. So on this one, we got some z in the area to the right. It's going to be 0.05. If I remember correctly, this is one of the ones where it's a little bit trickier. But so probably the shortest way we can do this is to just look inside the table for 0.0500. And then just remember that the thing we get out of the table is going to be on the left side, so we got to change the sign to make it on the right side. And this one, I believe, is one where it's exactly between two areas, which is a little unfortunate. But, let's see, 0.05. Yeah, we got two that are close. Negative 1.65 has an area of 0.0495. And negative 1.64 has an area to its left of 0.0505. So this is one of the unfortunate ones where the one we want is exactly between, so we add these together and divide by 2. We get negative 1.645. And then we want the one on the right. So we will have 1.645. Take the opposite. That one gets a little convoluted because it was exactly between two values. They're not always that long. Usually you can just look it up and then change the sign. Question on that one is a little longer, trickier. Yeah, okay. 16. Just looking up critical t. So it says for t, we've got an area of 0.025. I want that to be to the right of t. So that also tells us that that's going to be in one tail. And then our degrees of freedom equals 8. So on these, just don't, since we've been in the habit of having to calculate degrees of freedom, just realize it already gives you degrees of freedom. You don't have to subtract here. So we want, go to table C, we want 0.025 in one tail. That's the middle column. 8 degrees of freedom. Our critical T here is 2.306. Well, we've had quite a bit of practice with those. So. 17 may be a little fuzzier in your memory because it's confidence interval. So we've got a random sample of 11 fields of rye with a mean yield of 22.5 bushels per acre, standard deviation of 5.52 bushels per acre. Determine the 80% confidence interval. I would also let you know that this one is sigma unknown. It's a little hard to tell, they don't spell it out for us. So here, when we're looking for the critical value of the critical T, so on these, it's been a little while since we've done this. To get our critical T, we do 1 minus the confidence. That'll tell us we'll have 0.2 in 2 tails. Confidence intervals are always 2-tailed. We can say that now. It makes sense. Okay. And then degrees of freedom is the sample size minus 1. This one we've got a sample of 11. So we'll have 10 degrees of freedom. So our critical T um, 0.2 in 2 tails, so that is the first column, 10 degrees of freedom. Our critical T will be 1.372. And then step 2 tells us to finish making the confidence interval. So we need a margin of error formula. In this situation, here's our formula. So we've already got the critical T, 1.372. And then sample standard deviation is 5.52, that's S. Our sample size was 11. And then remember on these, we want to keep several decimal places for our margins of error. So then for my margin of error, I get 2.2, 8, 3, 4, and I'm going to round to 8, we'll keep 5. So 5 or 6 places is good. And then one more thing, we got the margin of error, so now we actually need to make the interval. So our mean, our point estimate, x bar was 22.5. Now we would do 22.5 plus and minus our margin of error. Get our interval, so let's see. We do minus to get the lower bound. It says round to 1 decimal place, so on the lower end we'll get 20.2. And then we add. On the upper end we'll get 24.8. There's our confidence interval. And these last few are stuff we just tested on, so hopefully they're fresher in memory. Let's see, got an engine valve. Says if the valve was designed to produce a mean pressure of 4.7 psi, is there sufficient evidence that the valve performs above the specifications? Our alternative would be that mu is, let's see, above the spec, which was designed to produce a mean of 4.7, so above 4.7. So our null would be that the mean equals 4.7. This one gives us sigma, sigma known. So our test statistic will be a z. So let's see, tested on 110 engines and the mean was 4.9, so 4.9 minus mu, which is 4.7, over our standard deviation was 0.8, divided by the square root of our sample size, which was 110. Let's see what we get there. I'm getting 2.62. My test statistic. Greater than points to the right, so this is a one-tailed test, but beyond that, it's right-tailed. So for my p-value, I'm going to look up the opposite. I'm going to look up negative 2.62. If I look up negative 2.62, I get 0.0044. Let's identify the level of significance. So let's see, it says, is there evidence at the 0.02 level? Alpha is 0.02. So here our p-value is smaller than alpha. So we reject the null hypothesis. And 19. Same thing, this is sigma unknown problem. That means we're going to have a t-test statistic on this one. This one wants to know if there's sufficient evidence that the bags are underfilled. So it says the setting was 409, so we get mu is less than 409. So the null would be mu equals 409. And to find our t-test statistic, we'll have, let's see, 13 bag sample where the mean is 401. So 401 minus 409 over our sample standard deviation is 28, divided by the square root of our 13 bag sample. Let's see what we get there. I'm getting negative 1.030. This one is not only a one-tailed test, it's left-tailed. And it says determine the decision rule, so what this is asking for the critical T. So we need degrees of freedom and we need to know our level of significance. So we had a 13 bag sample. We got 12 degrees of freedom. Our level of significance was 0.05. And since it's left-tailed, one-tailed, we're going to look for 0.05 and one-tail. It is the second column with 12 degrees of freedom. That gives us 1.782. And then one last thing, since we're on the left side, So I'll make this negative. So we want it to be on the left side. And then to make our decision, we're doing a left-hand test, so we got our critical T over here, negative 1.782. To the left of that is our rejection region. On this one, our test statistic was negative 1.030. That's over in the non-rejection region. So we failed to reject the null hypothesis. That's our test statistic. Just a couple more, I think. One more. And then we got a proportion one, and then a correlation problem, and that's all. So let's see. We got a publisher reports 45% of their readers on a particular make of car. Marketing executive wants to test the claim that the percentage is actually more than reported. So that would be that P is more than, greater than 45%. Null would be that P equals 45% or 0.45. For proportions, we only have one choice of test statistics. So there it's our sample proportion. It says a random sample of 320 found that 50% of the readers owned a particular make of car. So P hat is 50% or 0.5. So P hat minus P, 0.45, over big square root 0.45 times 1 minus 0.45. And that's over our sample size, which was 320. Let's see what we get there. I'm getting 1.797, so it's going to round up to be 1.80. This one is one-tailed, and better than that, it's right-tailed. So to get our p-value, we'll look up the opposite of our test statistic. So we'll look at negative 1.80. So for that, I'm getting 0.0359. Our level of significance, what was it? Was 0.1 or 0.10, however you want to write it. So here again, our p-value is smaller than alpha. We reject the null hypothesis. And only one more. Want to know if the correlation will be positive, negative, or if they're not correlated. And we got the age of a vehicle and the cost of maintenance. So this one may not be so good because if you're not real familiar with cars, you might not think about it. But The older a car gets, the more it costs to take care of it. And you have more things you have to fix on it. And so age is increasing, the cost of maintenance is increasing. Since they're both increasing, that one would be positive. And that's it. Am I having questions? So Wednesday will just be if you do have questions on this, or if you have stuff on Hawks you want help with, you can come in. Other than that, you're good.